Welcome back, Physical Science. This is the last booklet in the HT1, the Heat 1 section, and it looks at phase changes and ties that in with temperature changes. So here it just simply starts off with we're talking about the glaciers and there being a change in state due to absorbing heat, ice changing into water, and of course causing glaciers to retreat. So if we look at states of matter, of course solid, liquid, and gas are the states of matter. The kinetic molecular theory explains the difference between these physical states. So as we talked about earlier, in a solid state, forces of attraction hold particles very close together, almost fixed positions. So the only movement that is allowed is vibration of solid molecules. And they can't easily slide past each other. So they're held together because they're close together. They're not moving as fast as a liquid. Therefore, the only thing they're allowed to do is vibrate, and which makes solids rigid and maintain their shape. Liquids have more kinetic energy. So if a solid absorbs more and more heat, the particles move faster and faster, get further apart, and so there's more movement allowed. So the liquid vibrates more than a solid, and the molecules are allowed to slide past one another. And that gives liquids ability to flow and pour. And of course, if you add more energy to that, the molecules move faster and faster and faster, move further apart, and basically you have a gas being formed in which molecules expand to fill the container they're in, such as air inside a balloon or a tire, and causing pressure. So going from one state to another, solid, liquid, gas, increasing kinetic energy. But what happens right at that point when a solid becomes a liquid or a liquid becomes a gas, or vice versa? Those are referred to as changes in state. So when solids, liquids, and gases absorb or release energy, they may change the state. For example, a solid could change into a liquid and a liquid could change into gas. When a substance absorbs thermal energy, the particles of that substance move faster and go further apart, as I mentioned. Thermal energy is not really absorbed. It is simply transformed into moving energy or kinetic energy, and potential energy or stored energy. And this little diagram here kind of illustrates that. So solid versus liquid versus gas. As we can see, the particles move further and further apart when they absorb energy. If we were to go vice versa, gas slowing down to become liquid, slowing down to become solid, that must involve the release of energy. If we have to absorb to go from solid to liquid to gas, then we must release energy when going from gas to liquid to solid. Okay, and over here they have an example on this page, basically starting off with ice cubes and heating up until it becomes a vapor, and looking at the results. So here it's minus 10 degrees in this beaker of ice, of course, so we add heat to it. The temperature is negative 10. Of course, the ice absorbs thermal energy, so it begins to vibrate at that point. This warming up of the ice increases the temperature of the ice. As the particles absorb more and more energy, the force of attraction are not strong enough to hold it in fixed position, and eventually ice reach its melting point. So that point in which the solid turns into a liquid. Okay, at this point the solid begins to change to liquid. The melting point of water, of course, is 0 degrees C. This change of state is called melting, kind of the layman's terms of saying it, or fusion, also of what it's known as. Eventually all of the ice becomes liquid water. But notice, thermal energy continues to be added during the melting process, but the temperature does not change. So as you can see here, and you can actually do this. We add heat to it, the ice eventually becomes water, but the temperature stays the same, which means that addition of heat is not being used to increase the kinetic energy, because if it was increasing the kinetic energy, the temperature would go up, because temperature is a way of measuring kinetic energy. Okay, so what's going on there? Let's see here. As liquid water as it becomes water, it absorbs more energy. The particles move faster, go further apart. This warms up the liquid and increases its temperature. So we go from 0, 10, 20, 30, all the way up to 100 until it reaches its, of course, boiling point, if we're talking about water. So all the particles have enough kinetic energy to completely break away from each other. At the boiling point, the liquid water changes into a gas. So that is called the evaporation or vaporization state. And at that point of 100, it'll stay at 100, the water will, until everything becomes a vapor. then again the temperature goes up. So those specific areas of change in state, the temperature does not change. So the thermal energy that I'm adding from the Bunsen burner or hot plate is not increasing the kinetic energy. It's increasing, it must be, potential energy. So we go here, if you're doing this in vice versa, removal of thermal energy reverses the process. In this case, a gas cools down to a liquid, and a liquid cools down to a solid. Change of gas to a liquid is called condensation. So if liquid to gas is vaporization, the vice versa is condensation. And going from solid to liquid, we said was melting or fusion. Vice versa is freezing, or quite often it's known as solidification. And of course, in some cases, we can skip steps depending upon the temperature. Sublimation is going directly from solid to gas. Okay, so if we were to do this experiment, and like every minute note down the temperature, we might get a graph that looks like this, which is referred to as a heating curve, starting off at -10, melting, heating up liquid, vaporization, and then gas, or vice versa. Starting as a gas, cooling down until the gas turns into a liquid, then liquid, going down, liquid to solid, solid. So the change in temperature that occurs when a substance absorbs thermal energy can be shown on a heating graph such as this. You know it's a heating graph because the temperature is going up. Similarly, the changes in temperature that occur when substances release thermal energy can be represented on a cooling graph, which of course is this, starting at a high temperature and going down. In both graphs, the vertical axis, of course, is temperature, as you see, and the x-axis represents the energy being added. So we're starting off here, adding energy, adding energy, adding energy, or in this case, releasing energy, releasing energy, releasing energy. Figure 4 is a heating graph and cooling graph for water, so it shows what's going on here. So as you can see here, solid, liquid, gas, or gas, liquid, solid. The increasing lines or the decreasing lines represents a single state. So here we have solid, liquid, gas, or gas, liquid, solid. And the flat line regions represents a change in state. So ice melting, so solid going to liquid, liquid going to gas, gas going to liquid, liquid going to solid. So that's demonstrated by the flat line region. So you can see even here in the little visuals here, so this isn't solid, it's not liquid, it's kind of a transition between. Same thing here, not liquid, not gas, but a transition. So key things to note, on the heating graph, thermal energy is absorbed by the water molecules through the heating process. On the cooling graph, thermal energy is released because it needs to release energy to slow the molecules down so they get closer together to go from a gas to liquid to solid. Temperature changes occur only when one state is present. Highlight that. So warming up solid ice, temperature changes. Warming up liquid water, temperature changes. Warming up water vapor, temperature changes. So the temperature changes when one state is present. These changes are represented by the angled parts of the graph, as I mentioned. And the third point here, the temperature remains constant during a change in state because thermal energy is being used to change, it must be, potential energy. Remember, temperature is a measure of kinetic energy or moving energy. It's not moving energy that's being added, it's stored potential, getting enough energy to break the bond of solid to liquid. On a heating graph, this occurs when a solid changes into a liquid and when liquid changes into gas. On the cooling graph, this occurs when a gas changes into a liquid and when a liquid changes into a solid. This is represented by the flat line parts of the graph, of both graphs. The heating graph shows a distinct melting and boiling point, so those are the flat line regions. So the melting point is 0, and vaporization point or boiling point is up there, and of course vice versa. We'd have the condensing point and the freezing point, and of course they're identical. Melting and freezing are both at the same temperatures. The boiling point and condensing point are also at the same point, just going in reverse direction. So as I mentioned here, the heating graph shows the melting and boiling point. The cooling graph shows the condensation point and freezing point. Melting and freezing are both at 0. Boiling and condensation are both at 100. In general, melting and freezing occur at the same temperature, and boiling and condensing occur at the same temperature, so as I mentioned. So you may believe the temperature of a substance should change while it's absorbing or releasing thermal energy because thermal energy affects the kinetic energy, but of course the temperature is not changing in those flatline parts, those changes of state. So if we look there, during melting and boiling, thermal energy must be absorbed by the particles. Now here's what's happening here, folks. The absorbed energy is needed to break the bonds that hold the particles together. So if we're heating it, breaking the bond between the solid particles. However, during condensation and freezing, thermal energy must be released by the particles of the substance. The released energy allows the particles to move closer together and vice versa, form a bond of attraction. So if you're heating, you're breaking the bond, the attraction, to make them move further apart. When you're cooling, you're releasing energy, therefore everything slows down and come together and that force of attraction is felt. So in each of these situations, the change in thermal energy of the substance results in a change in potential energy. In other words, when a substance melts, boils, or condenses or freezes, the absorbed or released energy must be transformed into potential energy rather than kinetic. Since the kinetic energy of the particles does not change, that temperature is the same. So the thermal energy being added or released has to do with potential energy during those changes in state. Okay, in the second video we'll look at latent heat.